Hello, and welcome back to Chapter 8. We are going back to Section 8.1 today, and we're going to look at the matrices of systems of equations. I know we've already discussed, I've shown you how to do this in your calculator. This is the kind of work that you're going to have to do by hand. You can always double check your solutions using your calculator, but to solve matrices using systems of linear equations, we're going to have to do what we call the row echelon form, which we did do back in Chapter 7, and we're going to have to do the reduced row echelon form. Now, a matrix in row echelon form, if you remember, has any row that has all zeros in it has to occur at the bottom of your matrix. And if it doesn't, remember that we can shift these rows around, and we'll talk about this here in a little bit. And then for each row that does not have all zeros, the first entry has to be a 1 in the first row, then in the second row it will go 0 and then 1, and then in the third row it will go 0, 0, 1, and so on. And that's why for step 3 it says for two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. Now the one thing we haven't talked about yet is this down here where it says a matrix in row echelon form is in reduced row echelon form if every column that has a leading 1 has zeros in every position above and below its leading 1. And we will do an example with this here in just a few minutes. First of all, let's just sit here and review and look at example 1. We want to determine whether each matrix is in row echelon form. And if it is, then we want to determine if it's in the reduced row echelon form. So let's look at A. Remember, in row echelon form, I have to have a 1 in the first spot, which I do for the first equation, or the first row, sorry. In the second row, I notice that in my first spot here, I have a 0, which is fine. And in my second spot, I have a 1, so my leading 1 is here. And in the row above it, the leading 1 is farther to the left than the leading 1 in the lower row, so I still meet my requirements for being in row echelon form. Then if I go to my third row, I see that I go 0, 0, 1. So if I look above, I see that the leading 1 in the row above is farther to the left than this leading 1. So I would say that this equation here is in row echelon. Now, for it to be in reduced row echelon, I now have to go back and see for every leading 1, do I have a 0 above and below my leading 1s? And in this case, because of this 2 and this negative 1 above this one, I would say this is not in reduced row echelon form. So I'll say not reduced. Okay, now if I look at part B, I notice that I have a 1 in this for the first row here. In my second row I go 0, 1, 0, 2. Third row goes 0, 0, 1. And then I have leading 0, or all of my 0, the last row is all zeros. So in this case, all my zeros occur in the bottom row, which was a stipulation for row echelon. Then I see that I go 1, 1, 1, and it kind of goes down this diagonal. Every leading 1 in the row above is farther to the left. So I would say that this is in row echelon. Now to check for reduced row echelon, if I look at my leading 1s, in this case if I look at this one, I see that I have all zeros that occur below it. So that meets the criteria. Now if I look at the second leading 1, I have a 0 above and zeros below. So I'm still looking good for a reduced row echelon form. And my third leading 1 has zeros above and below as well. So this is reduced. Now for part C, I see that I have a leading 1 right here. When I go to my second row, I see that I have a 2 where I should really have a leading 1 there. So because of this 2, I don't even have to look any farther. This is not in row echelon form. Now, back in Chapter 7, we did use the row echelon form to solve our system of linear equations. Now, we can actually do the same thing, except we're going to use matrices instead of the systems. And really all that means is that we do not have to include the x, the y's, the z's, any of the variables that are associated with the system. So the first thing we're going to do is we're going to write the augmented matrix. Then we're going to use the elementary row operations. And if you recall, the elementary row operations, and let's write this down here. Your elementary row operations were to interchange rows, this is where if I would need to move a third row up to the top row, I can do that. So we'll say interchange rows. We can multiply a row by a non-zero constant. And we did this, if you recall, so that we can add two equations together to get a new second equation or a new third equation. And the third one would be to add a multiple of a row to another row. Okay, and again, this is just so we can cancel out a row or a variable. So these here are all elementary row operations. So once we use our elementary row operations, then we want to write the system of linear equations that correspond to the matrix, and then use back substitution to find our solution. So let's go ahead and look at example 2. The first thing we want to do is we want to put this in an augmented matrix. And remember, an augmented matrix means I'm going to take my coefficients. So I have 1 for x's, -2 for y, 3 for z, and we're going to do our dot dot, and then my constant of 9. I have -1x, 3y, 0 z's, and a -4, and for my constant. Then I have 2x, -5y, 5z, and a +17. So here's my augmented matrix. Now, to go ahead and start putting this into a row echelon form, I see that I already have my leading coefficient of 1. So at this point, I don't see any reason to change that. What I now need to do is I need to go and I need to eliminate this term here, and I can do that excuse me, by adding my first equation here and my second equation here. Now, I cannot stress enough to you, please make sure that you show me the work that you're doing. So when I do this, as I mentioned before, I'm going to leave the first row by itself. So I have 1, -2, 3, and this equals 9. Now I'm going to go R1 plus R2. So 1, and I'm coming up here, 1 plus a -1 is going to give me 0. -2 plus 3 here is going to give me 1. 3 plus 0 is going to give me 3, and this is going to equal 9 plus -4, which is 5. Now, to get rid of this 2 here, I see that if I multiply this row by a negative 2 and add it to this third row, then I can cancel those out. So let's go ahead and do that right now. So we said a negative 2r1 plus r3. Now if I multiply my first row by a negative 2, that's going to give me negative 2 then I'm going to have a positive 4 and a negative 6, and that's going to give me a negative 18. And I said I'm going to add that to R3, which was already 2, negative 5, 5, and 17. So when I add these together now, these are going to cancel. I end up with a negative 1, negative 1, and negative 1. So now I'm going to replace that. Oops, I wrote those in the wrong spot. So this here is going to be 0, negative 1, negative 1, and then equals a negative 1. Okay, as you'll notice, I have a leading coefficient, or leading 1 here. My next row down has a 0 below that leading 1, and then my second term over has a 1. Okay, so I have 2 leading 1s, which is what I want right here. So I don't have to do anything else to that second row, but now I see that I need to get rid of this negative 1 in my third row. So to do that, let's first start out by, I'm just going to rewrite my 1, negative 2, 3, and 9. And then I said I was going to leave my 0, 1, 3, and 5. And now I have to figure out how to get rid of this negative 1. Well, I see that if I add this negative 1 to the row 2's 1, I'm going to cancel those terms out. So again, I'm going to make note, and I'm just going to go R2 plus R3. And when I do that, I have 0 plus 0 is 0. 1 plus negative 1 gives me 0. Then I have 3 plus negative 1 gives me 2, and this is going to give me 5 plus negative 1, which is 4. So I don't have a leading coefficient of 1 here yet, but if you recall, I can divide everything in this row now by 2, and that will make this a 1. So when I do that, let me shift this down a little bit more. I'm going to rewrite my 1, negative 2, 3, and 9, 0, 1, 3, and 5, and now I'm going to go 1/2 R3, or R3 divided by 2, and that will give me 0, 0, 1 equals 2. At this point, what that tells me is that I have, based on this piece right here, this is really my Z column, or my Z row, so I just figured out that Z equals 2, and if I take that and I plug that up into this equation, remember that this is really 1y plus 3z equals 5. So if I go and I plug this z in here for this z, I see that I really have y plus 3 times 2 equals 5, or y equals a negative 1. So if z equals 2, y equals negative 1, and because I now know z and y, I can take this equation right here, and I know that that's really x minus 2y plus 3z equals 9. So when I go and I plug in everything that I know, I see that I have x minus 2 times a negative 1 plus 3 times z, which was 2, equals 9, I can see that my x then is equal to 1. So my solution is 1, -1, and 2. So this right here is the solution to my system. The last thing we're going to look at today is the Gaussian-Jordan elimination with a reduced row echelon form. Now the Gauss-Jordan elimination, if we continue to reduce this, I'll show you how to do this here in a second, you'll see that we actually won't have to go back and do the back substitution because everything will be laid out for us. So it is kind of nice to do the reduced row echelon form. So let's go ahead and look at the next example and I'll show you how to do this. Now example 3 says use the Gauss-Jordan elimination to solve this system. And this is actually the matrix that we came up with at the end of example 2. 1, -2, 3 equals 9, 0, 1, 3 equals 5, and 0, 0, 1 equals 2. Now what we're going to do is we're going to put this in what we call a reduced row echelon form. And if you remember from the beginning, the reduced row echelon form means that I will have zeros above and below any leading ones. So that I would be okay. If I look at this one here, I see that I have 2 zeros below it, which is fine. If I look at this leading one, I have a -2 above it, so I need to change that to a 0. And I'm already set here because I have a 0 here. And then I see with this leading one, I need to somehow get rid of these right here and make those zeros. So that's really our goal here in example 3. Once I've obtained that, then you'll see that I have what we call a reduced row echelon form, and then it will tell me that what z equals, what y equals, and what x equals without having to do back substitution. Okay, in this example, right now I see that I have this -2 right now is keeping this leading one from being, or meeting the requirements of being in reduced row echelon form. So an easy way to get rid of that -2 is to see what can I do to cancel this -2 out with this row. So if I multiply row 2 by a +2, then that's going to cancel out this -2 here when I add it to row 1. So again, I'm going to make note of what I did. I'm going to go 2r2 plus r1, and I'm going to make that my first row. So 2 times row 2 is going, or I'm sorry, we'll just go r1, which is 1, -2, 3 equals 9, and then I'm going to multiply my second row by 2. So that's going to be 2 times 1 is 2, 3 times 2 is 6, and 5 times 2 is 10. And when I add those together then, I see that I have 1, 0, 9, and 19. So I'm going to put that in for my first row now. So 1, 0, 9, and this equals 19. I can put in my second row already, which is 0, 1, 3 equals 5. And my third row was 0, 0, 1 equals 2. So now I see for my first leading one, I have zeros all below it, which is what I want. For my second leading one, I've got all zeros above and all zeros below. So we're on the right track. Now I come into the issue of having this right here. For my third leading one, I have 2 non-zero numbers above it. So I just now have to go ahead and get rid of those. Once I get rid of them, I should have a reduced row echelon form. So let's first look at how we are going to get rid of this 3. Okay, I see that if I multiply this row here by -3 and add it to this row, that my 3's should cancel out. So let's go ahead and do that real quick. We'll do this here in green. So we have 1, 0, 9 equals 19. Oops, we're going to multiply this. We said we're going to go a negative 3R3 plus R2. So when we do that, R2 is going to be left alone, so I have 0, 1, 3 equals 5. Then I have 0, 0, negative 3 equals a negative 6. So when I add these together, I have 0, 1, 0 equals a negative 1. So I'm going to write that row in right here. So 0, 1, 0 equals a negative 1. And my third row was already 0, 0, 1 equals 2. Now I see the only thing that's keeping me from being in reduced row echelon form is that 9 there. So let's go ahead and do this a similar type process. The only thing that's going to cancel out with this 9 now is this 1. So I'm going to have to multiply this 1 by a negative 9. And let's do that right down here. So we just said that we were going to multiply row 3 by a negative 9 and add it to row 1. So my row 1 was going to stay 1, 0, 9 equals 19, and we're going to multiply the third row, which was 0, 0, 1, by a negative 9. So that's going to give us 0, 0, negative 9 equals a negative 18. When I add these together, I get 1, 0, 0 equals 1. So I'm now going to go and plug that in. So 1, 0, 0 equals 1. My second row is 0, 1, 0 equals negative 1. And my third row is 0, 0, 1 equals 2. Now, if you recall, and you look back at example 2, we had to do back substitution. Here, I don't have to do that. I know that this 1 is really my z, so I just found that z equals 2. When I look at this row here, this 1 is really in my y spot, so I now know that y is equal to a negative 1. And from my first row, this 1 here is really in my x spot, so 1 equals 1. And I just solved that system without having to go back and do back substitution. And you can again verify this using your matrix functions in your calculator. So if you have questions on this, please let me know. Thanks.